Hello everyone, my name is Saman and welcome to Pi Nation Studio. So today we are going to have some fun with one interesting fact in mathematics that we have learned in high school. And this is my first ever video, so pardon my language, my handwriting, and definitely in future as well I'll upload some more interesting facts and let's start to have some fun with math. So, if you have studied set theory, or if you're in high school, like maybe in grade 10 or 11, you might have gone through these concepts. Like on set theory, we have different functions and we define relations and functions, and then the entire calculus stands on that. So, today we will see an interesting example of relations. So, let's begin. Let's say we have a set of math. So if you have studied set theory, or if you're in high school, like maybe in grade 10 or 11, you might have gone through these concepts. Like on set theory, we have different functions and we define relations and functions, and then the entire calculus stands on that. So today we will see an interesting example of relations. So let's begin. Let's say we have a set of natural numbers, like set of natural numbers 1, 2, 3, and so on, the numbers that naturally exist. Now, and we are also familiar with the Cartesian product of natural numbers. So that means set of all ordered pairs say that AB belongs to N. Define a relation R on n cross n such that two elements A comma B and C comma D in n cross n are related to each other, so that for all A comma B and C comma D belong to n cross n, we call them related to each other if and only if A plus D equals B plus C. So this is the definition. So we take any 2 points from n cross n. We call them, these 2 points are related to each other if and only if and only if they're all right. So if and only if this coordinate plus this coordinate is same as this coordinate plus this coordinate. Okay. Now we are going to prove that this relation is an equivalence relation. If you guys want me to define or teach or tell you what this Cartesian product means, or what a relation is, what is the equivalence relation or something like that, we can I can define those things or teach those things in other in some other video, but today we assume that we are familiar with this. Okay, now we are going to prove that this R is equivalence. In order to prove R is equivalent, we will first show that R is reflexive. For reflexive, we need let A comma B belongs to n cross n. Okay, and we know that if I add A plus B is same as A plus B, right? Or since addition is commutative, I can write A plus B equals B plus A. Oops, not C, it should be A, my bad. And so from here, if I see this picture, now I got A plus D equals B plus C. This would imply A comma B is related to C comma D. Similarly, I have something like this here, A plus B equals B plus A. I can write A comma B is related to A comma B. Hence, R is, so this proves that if you take any element in a cross sorry, you take any element in n cross n, you'll get that element is related to itself. So that's reflexive. So, and now we will prove that R is symmetric. Right. For that, we take two elements a comma b, c comma d in n cross n. Right. So a comma b, and in symmetricity we have one assumption like such that a comma b, any two elements in a, n comma n. In order to prove R is symmetric, we first assume a comma b is related to c comma d. In order to show it is symmetric, we will prove that c comma d is related to a comma b. We will reverse the order, which is like when I see the definition of the relation, it's like this definition. I think we can easily prove it. So let's see, a comma b related to c comma d, that means a plus d equals b plus c, and I can easily write it as, because addition is commutative, so I can write d plus a equals c plus b. All right. From here we got, so we can write it like this as well, and this clearly shows that c comma d is related to a comma b, right? So symmetricity has been proved. Now the third thing is we need to prove transitive. That relation R is a transitive relation. For that we take three elements a comma b, c comma d, e comma f belongs to n cross n, and the condition here is the first element is related to the second element and the second element is related to the third element. We need to show that the first element is related to the third element, which is nothing but a plus f equals b plus c, right? So we need to show this. So let's see. Now, seeing our condition a related to b, ab related to cd, that is nothing but a plus d equals b plus c, and similarly c plus f equals d plus e. Let's add these two equations. So we get a plus d plus c plus f equals b plus c plus d plus e, right? Which is nothing but, if we rearrange, or in other words, if I use commutativity, I get a plus f plus d plus c equals b. Let's rearrange this one as well, and we will get b plus e plus d plus c, right? Now if I can clearly see that I'm getting something like this here if I just cancel these two, right? In other words, if I subtract d plus c from both sides, or add minus d plus c both sides, right? But no, I'm not going to do that. Why? I'll show you at the end. Like, intentionally, I'm not going to use negative sign. I'm not going to use subtraction. So originally what we have set of natural numbers and this addition only. We are not going to use subtraction or negative numbers. So in order to prove this, let's see what we will do. All right, so let's get rid of these. So instead of, so this step is not correct. Instead, I'm gonna leave it here as e equals plus d plus c. So in order to prove that a plus f equals b plus c, we will use Peano's axiom, which is very similar to what we will actually do. Peano's axiom says if nth successor of two numbers are same successors, then those two numbers, the two numbers are also same. In other words, if x, y belongs to n and x plus n equals y plus n implies x equals y. So this is the Peano's axiom without using negative number, without using subtraction. So we will use that. So we can easily see that from here we will get a plus f equals b plus e. So this was intentional. I will explain why I use this Peano's axiom instead of like just subtracting. So this shows that a comma b is related to e comma f. So hence we prove that R is reflexive, symmetric and transitive. So therefore R is an equivalence relation. It's an equivalent relation. Now when we have a relation defined on a set and the relation is equivalent or equivalence relation, we can define equivalence classes. We can define equivalence classes. Just a reminder what the equivalence classes are. So I will define in the same manner. So equivalence classes are denoted by this square brackets. Is a set of all those points such that set of all those points in the same set such that a comma b is related to x comma y. So this is the equivalence class. Like equivalence class of one point is a set of all those points which are related to that point. So all these points which are related to a and a comma b would form the set of equivalence class. So let's take some examples. For example, we take 1 point. We are going to see some examples here. 1 comma 1, the equivalence class of 1 comma 1. Now you can see it, you can check it, but the elements which are related to 1 comma 1 would look like 2 comma 2, 3 comma 3, 4 comma 4 and so on. You can check easily that each of these elements are related to 1 comma 1 and they are related to itself as well, because R is reflexive, symmetric and transitive. Similarly, if I take another example, equivalence class of 1 comma 2, so we will see the elements would look like 2 comma 3, 3 comma 4, 4 comma 5 and so on. Okay, let's take another. Let's say I take 4 comma 7. Let's do something like this. So any element which is related to this, it would look like 1 comma 4, 2 comma 5, then 3 comma 6 and so on. Okay, let's take some more examples. I'm gonna take two or three more examples and explain why I'm doing this. It is very interesting. So let's take 2 comma 1. So this way Elements would look like 3 comma 2, 4 comma 3, 5 comma 4, and so on. Similarly, let's take 3 comma 1. We'll get 4 comma 2, 5 comma 3, 6 comma 4, and so on. You want to take another example? Okay, let's keep these few examples. Now I can see that these are some ordered pairs, so I can plot these points on a Cartesian plane. All right, so we have a Cartesian plane here, and let's see what it would look like when we plot these equivalence classes. So we'll plot these equivalence classes one by one. So we start with the first one, 1 comma 1. So I'm gonna plot 1 comma 1, that is somewhere let me make it bold, somewhere here, right? Then 2 comma 2 would be somewhere here, like this, right? And if I join these, let's try to join these. So this would look like something like that, and something like, oops, this is very thick, let's make it thin. Right, something like this, right? All right, now let's draw the second one. Let's plot this. So this would look like 1 comma 2. So this is somewhere here, right? This, and then 2 comma 3 is somewhere here, 3 comma 4 is here, here. Let's join this one as well. So this would look like something like this, right? Now let's do the third one. So third one will look like 1 comma 4. So it is somewhere here, and then 2 comma 5 somewhere here, 3 comma 6, this, and so on, right? And we can join this one as well. Let's do that. So this would look like something like this, right? And let's plot 2 more lines and I'll explain. I think you are getting where I'm going, but let's see. Next, let's plot 2 comma 1. So 2 comma 1 is here. I'm getting here, 3 comma 2, 4 comma 3, this and this. Let's differentiate it with a different color. So selection of colors is not intentional, it's just, a random thing, something like this. So line is like slightly below the plotted points, but that's okay. So let's do the last one. Let's plot 4 comma 2. So this is somewhere here, 5 comma 3, this, and got this. And let's plot, let's like join these. So this would look like something like this. Now when we observe these lines, what do we see here? We see a pattern here. We see that the equivalence class of 1 1, the very first equivalence class, this, when we join all the points, this pass through the center of the Cartesian plane, and I can easily say that this entire line represents 0. It passes through 0. Similarly, 1, the second equivalence class, when I join all the points, it passes through on y-axis at 1. The third equivalence class 4, 7 passes through 3. Similarly, 2, 1, the fourth equivalence class passes through -1. This, the last equivalence class, passes through -2. So here what we can conclude that a relation defined on set of natural numbers based on just addition gives us the representation of integers. Let me use the correct way. This represents 1, this represents 2, this represents -1, this represents -2. So these equivalence classes are nothing but the integers. How crazy is this? So I just randomly, not randomly, it was a selective thing. We define a relation on set of natural numbers using just addition, that a comma b related to c comma d, say that a plus d is equal to b plus c, gives us the representation of integers. These are nothing but the equivalence classes of the relation we defined on n cross n. So this relation is very interesting. I know, like, you might be getting this thought that this is like something random, or maybe just a theoretical thing. Okay, we represent, okay, these lines are passing through these points. For example, I can again plot or define one more we can define one more equivalence class, something like 5, 1. This doesn't look like 5, pardon my handwriting. 5, 1. So this equivalence class would be like 6, 2, 7, 3, 8, 4, and so on. If we notice one thing, and if you also notice this thing, this is nothing but this is nothing but b minus a equals d minus c. So the 2 points are related to each other. Now we know that they represent integers and the negative sign is introduced. I can also rewrite it as in this way, that 2 points in the Cartesian plane are related to each other if and only if the difference between the y coordinate and the x coordinate is same. The difference between the y coordinate and the x coordinate is same. So similarly, I can plot this. What's the difference between 5 and 1? -4. So this line would go through here. So this is something like, it will go through here. Let's draw this. It will go through here. Something like this. And this represents -4. This represents -4. See, this equivalence class represents -4. How crazy is this? Natural numbers, a relation defined on natural numbers based on just addition, gives us the entire entire set of integers. So this is called the construction of integers from natural numbers. So we just constructed the integers from natural numbers using relations. Thank you. We have another interesting we have another interesting example or creation or application of this relation. Very interesting. So this, all right, so we constructed the set of integers from natural numbers using a relation. Definitely, like, integers didn't came like this. It was not discovered based on this. But how crazy is this, that using natural numbers, just addition, we defined a relation on it and we constructed integers. Now what, like, so what, does it have the actual and any actual application in the real world? Yes, it does. So this relation that we defined here is very interesting. This gives us a very important application. So I'm gonna give you the more interesting application of this relation, the time zone. Time zone is defined, is based on this relation. How? So we define, so just a background, the time zone is like, if I'm in any point on the earth, and here if it is like 1 o'clock afternoon, it doesn't mean that it will be the same time on any other point on the earth. It will be a different time based on the position of earth and sun, right? So that's how we define the time zone. But how this simple relation defined on n cross n defines or gives us the definition or the practicality of the time zone, gives us the actual time zone. Let's see. So we define time zone relative to prime meridian, UTC, right? Prime meridian. So usually we write it as like UTC plus 0.00. So that's the main reference of all the time zones. So I'm going to define a set. Let A be a set 0 comma x and y comma 0, like set of these kind of ordered pairs, such that x and y belongs to this set, this closed interval 0 to 12. Taking 12 was intentional, just giving you a hint that time, the one entire rotation takes 24 hours. So 12 of these hours and 12 of these hours. So I took this in ordered in this interval. It's a set of like real numbers, every real number between 0 and 12, so that we cover each and every single point on the earth, right? And now I'll be defining the same kind of relation, R be a relation on A defined as A comma B related to same C comma D if and only if A plus D equals B plus C. The only thing is, for all A comma B, C comma D belongs to R. Oh, sorry, belongs to A. Right? Yes, we know that the representation of A and B is in the form of 0 comma x or y comma 0. Now we just define, and you can again prove that R is equivalence relation. So we can define again equivalence classes. Here we will I'm not going to like prove everything again. I will just come to the equivalence classes. Now let's see couple equivalence classes here. So most of the equivalence classes are of this form, 0 comma x and x comma 0. most of the equivalence classes are in this form. So taking just one simple example, equivalence class of 0 1. So equivalence class of 0 1 would be all places on the earth where sun rises 1 hour after UTC plus 0. So which represents all the places where the sun rises 1 hour after, so we define them as UTC plus 1. So you take 0 2, similarly will be all the places plus 2. In other words, similarly 1 comma 0 would be like UTC minus 1, or you can 0 0, you can put decimals as well. So using the same function, using the same relation, a very simple one, just giving the relation between the difference between these 2 points. If they are same, they're going to be related to each other. Similarly, using the same relation, we define the time zone. Thank you.